Ian would like to do any kind of introduction before I start.
Sure, I can give a very brief introduction. So I was extraordinarily lucky to meet Jason Wyenberg shortly after I arrived at the University of South Dakota. And I was very sad to not be able to convince him to move when I moved. I know it's not the easiest thing when your advisor leaves in the middle of your PhD, but Jason managed to figure out how to do it and has succeeded beyond my expectations. And I'm very excited to hear his talk today about his dissertation, Beyond Standard Model Interaction Portals of Neutrinos and Dark Matter Particle Candidates.
Great, thank you, Ian. So yeah, Ian kind of summarized the last couple of years. A lot has happened, and we all know a lot has happened since I gave my comprehensive defense about a year ago. But the show must go on, so they say. So my name is Jason Wyenberg. I'm a PhD candidate. Today's talk, as Ian said, will be titled Beyond Standard Model Interaction Portals of Neutrinos and Dark Matter Particles. I'll provide a theoretical motivation for my work, an excluded parameter space for the models, and a signal interpretation of the xenon one-time excess events. Just a few notes about the presentation. On the top right of the slides, there'll be a thesis page number. So for those of you who have an electronic copy of my thesis, this presentation will follow pretty closely with that, and you can refer to that those page numbers. There's no references shown on the PowerPoint slides themselves. So if you want to look at a reference for my work, you can go into the thesis page and follow the reference there. All right, so a brief overview of what I'll talk about today. So we know that the standard model is incomplete from a few phenomena. So one is the fact that neutrinos have masses and neutrino oscillations, the presence of dark energy and dark matter, the matter-antimatter asymmetries in the universe, to name a few. Some potential explanations for some of these anomalies are some interaction portals beyond the standard model. So my role as a theorist is to look at new ideas for new interaction portals, try to interpret how they might be visible in an experiment, and provide motivation for searching for these new interaction portals. Today I'll talk about 3 beyond standard model portals, beyond standard model interaction portals. The first is a generic dark matter standard model cross-section in which dark matter and standard model particles are coupled through a Feynman diagram that we don't know all the details of. The next is a more specific model in which a neutrino dipole interaction portal mediated by a photon can allow a neutrino to upscatter to a heavy neutral lepton state. The third is a dark matter neutrino portal mediated by a scalar particle in which scalar particle couple, oh, we got some feedback. Good, okay. So a portal in which the scalar particle couples dark matter and neutrinos and can also couple to the standard model quarks. I'll provide a summary of some future extension of my research I hope to do, and a conclusion and time for questions. So what is the theoretical motivation for my work? One big factor in looking for beyond standard model interactions is the dark matter problem. So we're all pretty familiar with the dark matter problem, but I'll provide a succinct summary of it. So in the 30s, Zwicky and Smith analyzed the Hubble telescope's galaxy cluster redshift data. Zwicky applied the virial theorem to the galaxy redshifts, and he found that using the virial theorem, the velocity dispersion was much larger than the calculated by the virial theorem from the potential energy of the luminous matter. It seemed as if there was some missing matter there that was non-luminous. This was a first indication of dark matter being present. The problem persisted, and then in the 1970s, Vera Rubin and Kent Ford did their famous analysis of galactic rotation curves. So they looked at the velocity of stars as a function of their radial distance from the center of galaxies. And they found that the stars that were far out from the center of galaxies were moving much too quickly than you could explain by the luminous mass. So it seemed like there was some extra matter holding them in orbit, preventing them from escaping. The current outlook is that there are many theoretical candidates for what these particles could be. Many have been ruled out and many still remain. There's active searches for these theoretically motivated particles through direct detection, astronomical observations, accelerator data, and others. The allowed parameter space of these particle candidates has been narrowed over the years through constraints by astrophysical data, early universe formation simulations, galaxy formation mechanisms, detector searches, accelerator byproduct, and many others. One particularly promising dark matter candidate is a WIMP candidate. So WIMP is a weakly interacting massive particle. And what's particularly exciting about WIMPs is that if you look at the early thermodynamics of the universe, WIMP particles could have been present in a large abundance. And then as the universe expanded and cooled off, their production rate could have dropped off, and their annihilation rate was such that their number density was decreasing in the early universe. But then at some point when the universe expanded such that the Hubble rate exceeded that of the interaction rate for annihilation, the relic abundance of the dark matter could have frozen out at a certain relic abundance. And the so-called WIMP miracle of this particle is that if the WIMP particles are on the GeV mass scale range and they have an interaction strength of the order of the weak force, they could have frozen out with the correct relic abundance that we see today in the universe through our observations, gravitational observations of dark matter. Some more details on the astrophysical constraints for dark matter models. Gamma ray production from dark matter annihilation. So if you have a model that postulates dark matter could annihilate and create a photon, if we try and search for that model, we look in overdense regions of dark matter in the universe. So the center of galaxies, the core of stars, and we should be able to see some signature of photons being created with high energies, gamma rays. The fact that we don't see those allows us to put some constraints on the interaction strength of dark matter. Other models could postulate an interaction in which dark matter has other predicted collision byproducts, so neutrinos or other particles. And the null result of looking for searches for those particles also allow us to put constraints on the interaction strength. A famous constraint is provided by the famous picture of the bullet cluster. So this is a picture that Hubble captured of two galaxies that seem to have passed through each other. So the two galaxies from the Hubble data, you can see from the luminous matter, it seemed like the two galaxies have already passed through each other, and the luminous matter of those two galaxies seem to have collided and interacted, primarily hydrogen, gas, and dust. But if you look at the gravitational lensing of that data, you can see that the majority of the mass is non-luminous, and it seems to have, the two galaxies seem to have passed through each other with very little interaction. That allows you to put some constraint on the self-interaction of dark matter. So if these two galaxies pass through each other and there is very little sign of them interacting, you can constrain how strongly the dark matter particles themselves would have interacted. Another wealth of data is, or a source of wealth of data is the cosmic microwave background. So in the early universe, as the universe was cooling off, electrons and protons, as they got cool enough, they were allowed to bind, and the universe became electrically neutral. At that point, photons were allowed to free stream. They were no longer colliding into electrons all the time. That so-called surface of last scattering created the cosmic microwave background, and that occurred about 380,000 years after the Big Bang. If you do a power spectrum analysis of the isotropies, or of the anisotropies of the CMB spectrum on different scales, you can find a wealth of data about the early universe at that time. So looking at the peaks on the power spectrum, where they exist and their amplitude tells us a lot about the dark matter, or a lot about the CMB at that time, but some signature of the dark matter density. A well-known plot that shows all the constraints from these from experiments is shown here. So this is a plot that shows the parameter space of a generic model of a WIMP particle of a varying mass versus its cross section, WIMP nucleon cross section. So this parameter space has some curves on it which show the excluded regions provided by data from experiments. So the exclusion curves show a line which shows above that line, that parameter space is excluded by that experiment. So for example, for the Lux 2013 line, if you look at, that's a green line kind of in the middle of the plot. If you look at a 100 GeV mass particle, and you follow that up to the Lux 2013 line, that data point shows us that at approximately 10 to the minus 45 centimeters squared, if the interaction strength were of that order or higher, the Lux data would have excluded it. You notice that all these curves seem to curve up at low WIMP masses, so about 10 GeV or a little less. This is due to the fact that there's a limitation on the recoil energy threshold of the experiments, so they can't see below a certain recoil energy. And I'll talk a little bit later about the importance of performing additional experiments to lower that recoil energy threshold. And And then a very important feature of this plot is the orange shaded region on the bottom. So there's a thick orange line, and that's the so-called neutrino floor. That's the point at which, if you were searching for a dark matter particle with that interaction cross-section, you would start getting background noise from neutrinos. So that's a hypothetical floor below which it would be very hard to look below. And I'll explain that in a little more detail as I talk about my current research. So that was just a summary of the existing kind of state of affairs of dark matter and beyond standard particle physics. I'd like to first talk about one interaction portal that I looked at first. This is a generic model. So I've got a Feynman diagram that just shows kind of a very generic model in which a dark matter particle and its antiparticle come into some kind of features of a Feynman diagram, and then a standard model particle and its antiparticle come out. So this is a very generic model. So on this Feynman diagram and all the Feynman diagrams I'll show, just FYI, the space is the vertical axis and time is the horizontal axis. A specific example of what this model might be is if dark matter could annihilate to a photon and interact and scatter off of, or interact and create an electron-positron pair. So this kind of a mechanism could actually be accommodated by the relic dark matter abundance through thermodynamic mechanisms, either through thermodynamic freeze-in, which is a little different than what I talked about earlier, and through an asymmetrical thermal freeze-out. What I'm going to talk about shortly is the possibility of dark matter scattering off electrons in a specific experiment. And the reason I want to talk about this is if we look at the total event rates in a typical, in an ideal germanium detector, we can look at what the event rates would be for dark matter scattering off electrons versus nucleons. So the blue curve here shows dark matter scattering off electrons. The red curve shows dark matter scattering off nucleons. The interaction cross section is just taken to be a generic value of 10 to the minus 44 centimeters squared. So we're just using this value to compare the rates of electron scattering versus nuclear scattering. And what's interesting about this plot is on the horizontal axis, which is the potential mass of the dark matter particle, for nuclear scattering, you can't see any evidence of dark matter particles if their mass is too small, below several hundred MeV or below a GeV or so. The red curve cuts off there. But below that, you can go several orders of magnitude lower in mass if you're looking for electron scattering. So this is like if you're trying to see evidence of a new particle, and the particle is like a ping pong ball, and you throw it at a bowling ball, you try and see if the bowling ball moves. It's very hard to do. That would be the nuclear scattering example. But if you try and see a ping pong deflect off another ping pong ball, which would be an electron, which is 1/2000th the mass of a nucleon, it may be easier to see the deposited energy. I'll talk a little bit more about why the rates for nuclear scattering are enhanced and higher than electron scattering at higher masses in a little bit. To do an event rate calculation of dark matter electron scattering, we have to have an understanding of the local dark matter density and velocity profile. So we use the standard Gaussian distribution. The curve is truncated above a certain speed. So we assume that if the dark matter was moving above the escape speed of our galaxy, faster than that, it would have escaped by now. But below that, the distribution profile of the velocity of dark matter is given by a Gaussian with a few parameters. The parameters are the mean speed of the dark matter, the escape speed of the galaxy, and our velocity through the galaxy. An important, so the parameters in this, we chose fixed parameters, but a little later I'll talk about what happens if you change these parameters and see how that affects our calculations. An important calculation is the mean inverse velocity. So if you integrate this velocity profile or velocity density with respect to 1 over the velocity, that factor is important when you go to a rate calculation. So dark matter electron scattering rates can be calculated. First, we'd have to calculate a differential cross section for the interaction. So we're using a value of a fixed cross section, which kind of parameterizes the strength of the interaction. That's the sigma E in this formula. And then to calculate the differential cross section for the scattering rates, you have to do an integral over the momentum transfer of the interaction. So if a dark matter particle comes in and scatters off an electron, there's a way of kind of encoding the whole wave function structure of the germanium atom in this parameter called F ion in this equation. So this F ion we actually took from some other people's work in which we were able to import their data on it basically encodes all the information about a wave function, the likelihood that a dark matter particle of a given momentum would scatter into a new momentum. You can do this integral and calculate the differential cross section and then combine that with the number density of dark matter and calculate a total differential scattering rate with respect to the recoil energy. And you get a plot that looks like this. So this plot shows dark matter scattering off electrons, the differential rate of scattering with respect to the recoil energy. There's multiple curves here, so there's kind of a lot going on. The black curve, which is just a horizontal line near the top, that shows the potential background from neutrinos scattering on electrons, and I'll talk about that a little later. The colored curves show the potential signal of dark matter particles scattering on electrons in a germanium crystal. The colored curves all represent different potential masses of dark matter. You can see as the mass of the dark matter gets smaller, so for example, the purple curve is the largest dark matter mass in here, that's 500 MeV. If you go to the blue curve, which is 5 times smaller in mass, that's 100 MeV, the event rates increase. And that's primarily due to the fact that the number density of dark matter is inversely proportional to the particle's mass. So we know the mass density of dark matter around us, but we don't know the mass of the particle. So if the particles themselves have a higher mass, the number density would be lower. So that explanation kind of explains the first 3 curves, the purple, blue, and green curves. But then when you get to low enough masses of dark matter, then you run into this issue that the recoil energy, the rates for recoil energies get truncated for higher recoil energies due to the fact that an incoming dark matter particle of a certain mass would not have enough energy to deposit an observable recoil energy in a detector. So the rates here kind of show how when you get down to about 5 MeV, the rates are really getting truncated. When you get down to about 1 MeV, those are a dark matter mass. You could have a really hard time seeing that in a detector. Dark matter can also scatter off nucleons. If we use the same kind of model, generic cross-section, the event rates can be compared. It's important to note that if the dark matter is scattering off nucleons with these energy levels, they're not probing the structure of the nuclei, so there's a coherent scattering effect. So the scattering rate is enhanced by an A² factor. And we can look at event rates on a similar plot here, which shows the differential event rates as with respect to the recoil energies. Again, the black curve represents the background. This is neutrino nuclei scattering from primarily solar neutrinos, which I'll talk about right away. The signals are the colored curves. These rates show how the scattering of dark matter off the nuclei of germanium produce event rates that are much higher than the electron rates, but drop off very quickly as the dark matter mass gets smaller than a GeV. I'll show this data on another slide shortly again. So the relevant backgrounds for this search are the solar neutrino fluxes primarily. So the solar neutrino fluxes have different sources from the different reaction chains in the sun. The PP mechanism neutrinos have the highest flux rate, but their energy levels are small enough that they don't really affect this particular search. When I talk about another model later on, they will affect it. The primary background for this model are the B8 neutrinos. So they have high enough energy levels and high enough fluxes that they could potentially be a background to our signal. So you can calculate what that background rate is with a calculation of the differential cross-section for neutrino scattering off electrons in a germanium atom. So there's a lengthy formula here. Some important notes about it. There's G, V, and GA constants. Those are the vectorial and axial coupling constants. GV is modified by +1 for electron neutrino scattering. So the scattering event rates are slightly different for electron neutrinos as opposed to muon and tau neutrinos. We can calculate a differential scattering rate similar to what I did for the signal earlier. We can also look at backgrounds from neutrino scattering off nuclei in the germanium. These rates are a slightly different formula. In this formula here, there's the Fermi constant GF, QW is the weak nuclear hypercharge, and then the F² is the form factor of the that's used for the calculation. We use the Helm form factor. Sparing all the details of those calculations, we put them all on one plot, which summarizes things pretty well. So there's a lot going on this plot here, so I'll spend a little time talking about it. The black curves provide event rates for the backgrounds from neutrinos scattering in a detector. The colored curves represent a signal rate from dark matter particles scattering in the detector. The dashed curves represent scattering off nuclei or nucleons, and the solid curves represent scattering off electrons. So you can see if we first compare the background rates for nuclear scattering versus electron scattering, the dashed line, which is nuclear scattering, has much higher event rates than the electron scattering. So the background rates from nuclear scattering of neutrinos is going to be much higher than electron scattering. For the signal rates, you can also compare the nuclear versus electron scattering pretty easily in this plot. So the purple curve shows, for example, if dark matter had a mass of 500 MeV, what would the event rates look like for electron scattering versus nuclear scattering? The dashed purple line shows nuclear scattering, and the solid purple line shows electron scattering. And you can see that the event rates are much higher for nuclear scattering, and that's primarily due to the coherent factor of the scattering. If you look at lower masses of dark matter, however, the advantage for looking for electron scattering is seen pretty soon. So if you go down to 100 MeV dark matter particle, the nuclear scattering rates drop off above about 2 electron volts. So that means 100 MeV dark matter particle could only deposit about 2 electron volts in a germanium detector from nuclear scattering. But if you look at the orange curve that shows a 5 MeV dark matter particle, the scattering rates for that particle to scatter off electrons, which is a solid orange curve, actually go up to much higher energy levels. So even though it's a 5 MeV particle, so still 1/20th the mass of the 100 MeV particle, the electron scattering rates go up to much higher recoil energies. If we want to look for the discovery limit of a detector, so how much, what's the kind of lowest cross-section a given detector could see for a given exposure, we can look at a plot like this, which shows on the horizontal axis the exposure of an ideal germanium detector. On the vertical axis is the cross-section that detector could see, so the discovery limit of that detector. The colored curves show different potential dark matter masses. The shape of the curve is what I want to point out here, and that's the fact that the discovery limit of a detector is really directly related to its exposure. So there's an inverse relationship between the detector exposure and the cross-section that detector can see. And that relationship holds until you get to high enough exposures upon which the neutrinos start becoming a relevant background. So the detector, kind of the return on investment for a detector, transitions from an exposure to the -1 regime to an exposure to the -0.5 regime. This qualitative plot here shows how if we want to kind of define a floor for detector searches, we can kind of define that around the region at which the detector will start seeing neutrinos, and in which it transitions to the regime of a MT, or exposure to the -0.5. I've dubbed this the so-called soft floor, so it's about 100 kilogram year exposure at which a detector is going to start seeing neutrinos. So we're going to keep this in mind when we look at discovery limits for detectors. Some important features of a detector that you need to be concerned about are the energy resolution of the signal that can be measured. So if a dark matter detector is looking for electron recoils and it can see very detailed recoil energies, so a very good resolution of the recoil energies, there's kind of, it has a better ability to distinguish over background the signal. If it cannot see the fine details of an energy profile, so if it can't see finer than about 10 electron volts, the advantage of having a unique signal from electron scattering is kind of lost. That's kind of like if you're looking at a picture and the picture is very fuzzy, so if you improve the resolution, you can see the picture better. So that's my son's kindergarten picture, Charlie. Another important feature of a detector is the is the minimum recoil energy threshold of the detector. So if a detector cannot see very small recoil energies, it could potentially have a lower discovery reach. It's important to note that for dark matter electron scattering in a germanium, the germanium detector, the rates are peaked around 6 electron volts. So if the dark matter can't see those levels of recoil energies, its ability to distinguish the signal will be diminished. Another boundary to consider is the fact that germanium has a band gap energy of 0.67 electron volts. And at that level of recoil energies, that means that if dark matter has a mass less than 1 MeV or so, germanium detector could not see it without additional techniques such as doping to lower that band gap energy. Dr. May at the University of South Dakota has done some research onto that. So this is kind of like if you're looking for a minimum recoil energy threshold. If you're looking at a picture and you can't see the dark parts of the picture, you can't see the picture very well. So here's 2 pictures of my daughters, and if you're able to brighten up the pictures and have a better threshold, you can see them better. So my daughter Thea and Lily. Another important feature of your model or of your detector is the model you use to analyze what happens when energy is deposited in it and it gets converted to a signal. So if dark matter scatters off a nuclei and it creates or it deposits some energy in the detector, how will that energy get converted into a usable signal that you can measure? And we use the Lindhard quenching model of deposited energy to an ionization signal. It's important to note that this model has some fairly large uncertainties at low recoil energies, both in how it operates and in the parameters. So I'll talk later on about how some future research could improve our understanding of the Lindhard model. But you can see on this plot here, it shows a comparison rate of the signal rate for a dark matter signal, which is the colored curves, as opposed to the background rate from neutrinos. And for nuclear scattering, our understanding of the signal rate of the background is limited by our understanding of the model of the conversion rate from recoil energy to signal. So there's 3 gray lines there on the top that show the different kind of models being used to go from a model of the incoming recoil energy to the signal rate. And each one of them have quite different rates, especially at low recoil energies, which is an important area where we're trying to look for a signal. Another very important characteristic of a detector is whether it can distinguish between electronic and nuclear scattering. So as you may remember from the earlier slides, the nuclear scattering rate for neutrinos is much higher than electron scattering. So if you can veto all nuclear scattering event rates, you can lower your background noise by several orders of magnitude. So this is kind of like if you're looking at 2 pictures that are overlapped and you try to look at the nuclear and electron scattering separately, you can see that they're actually what the 2 pictures actually are. So myself and my twin brother. Putting that all together on a single plot, this plot shows the discovery limit of a germanium detector. Neglecting the width of the bands for the moment, I'll come back to that later. The features of this plot are, so there's 4 curves shown. The blue and the green curves represent your discovery limit of a detector if the detector has no ability to distinguish between nuclear and electron recoils. The red and the orange show if the detector can distinguish between electron recoils. So you can see that the detector reach is improved by a couple orders of magnitude by being able to distinguish between nuclear and electron recoils. The difference between green and blue and between orange and red are the model of the form factor of dark matter. So this model can, I talked so far just about a generic model that didn't deal with the details of the Feynman diagram. But if the kind of form factor of the interaction, meaning the mediator particle on the Feynman diagram is like a heavy mediator particle, then the form factor is 1. If it's a light particle, the form factor is a 1/q² relationship. So the shape of these curves and their position on this plot are interesting in that they are changed by the specific model that you use. So to calculate these discovery limits, we use the log likelihood method. This is a method by which you run a whole bunch of simulations of experiments. And if you postulate that dark matter has a certain interaction cross-section, then you can run an experiment and simulate an experiment and see how many events would be possible in your detector. What you do then is you compare the signal, the likelihood of seeing the data of the signal to the likelihood of seeing that data just from systematic or statistical fluctuations from a null hypothesis. By comparing those 2 likelihoods, you can generate a test statistic, and then that maps to a chi-square distribution, and you can generate a statistical significance of an experiment. So if, for example, we look at this plot, which we looked at earlier, the discovery reach of a detector as a function of exposure these curves, all the points in these curves show a point at which there is a 90% likelihood that if dark matter had this specific interaction cross section, you'd see a 3 sigma statistical significance of discovery. Another way to look at this plot, maybe a little more enlightening, is instead of having exposure on the horizontal axis, this shows the same data but with dark matter mass on the horizontal axis. So this is the discovery limit of a germanium detector through dark matter electron scattering for various dark matter masses. So that's the horizontal axis and then various exposures. And you can see, obviously, as the exposures increase, the discovery limit lowers for the detector. Each of these colored lines are they're all 1 order of magnitude separate in exposure. So if there were no neutrino backgrounds, all these lines would directly map to a 1 order of magnitude improvement in the discovery limit as well. But as you follow these curves down, the separation between the 2 lines, so between the red and the orange, it's nearly 1 order of magnitude. But then when you get to the separation between the blue and purple curves, it's about half an order of magnitude. That's due to the fact that neutrinos start contributing to the background. A so-called kind of way of parameterizing the neutrino background I mentioned earlier is this way of calling it a soft floor. So experiments which have about 10 to the 2 or 100 kilogram year exposure are probing that soft floor. Some other important parameters that are contributing to our model are the astrophysical parameters of dark matter. So 3 of the main factors that have a big influence on our discovery reach of the detector are the mean speed of the dark matter, V naught, the escape speed of our galaxy, and the dark matter density, the local dark matter density at the Earth. These parameters have some uncertainties to them, so to parameterize how much they affect our results, we calculated an optimistic and a pessimistic curve for each of these 4 curves here. So this is the plot I showed earlier, and the width of those bands are defined by an optimistic and a pessimistic case of the astrophysical parameters. So the optimistic case is that dark matter has a very high density, so on the higher range of our uncertainty. The escape speed of the galaxy is very high, so there's still some very highly energetic particles around. And the average or mean speed of the dark matter is high as well. The pessimistic curves represent the opposite, so a low dark matter density, a low escape speed, and a low mean speed of the dark matter. So the optimistic sense, or the optimistic scenario represents the bottom of those curves, and the pessimistic scenario represents the top of those curves. Okay, so the second model that I looked at was a neutrino dipole portal. So this is a model that postulates that there's a coupling between the standard model left-handed neutrinos and through a photon, the electromagnetic field strength tensor, they can couple to a heavier neutral lepton state. So the Lagrangian here has a parameter D, which kind of that parameterizes the strength of this interaction. And then the new L is the standard model left-handed neutrinos. And they couple through a photon, which is represented by the gamma matrices, and the electromagnetic field strength tensor to a heavy neutral lepton state. This model, which we postulated, you can look for this model in existing direct detection experiments. So look for the signature of a neutrino coming in to a detector, depositing some energy, and then upscattering to a heavy state, which decays outside the detector. We looked at the xenon 1 ton experiment data, so the nuclear recoil energy data that was published by xenon 1 ton, which had kind of a null result. We were able to use that to put some competitive constraints on this interaction portal. Then subsequently, xenon 1 ton released their electronic recoil data, and there was a potential signal in there, so we were able to interpret that with this model and generate a statistical significance of this model to interpret the data. So I'll get into the details of that shortly. So the Feynman diagram we're looking at here, so instead of a generic model like I did in the first example, this is a more detailed model where we actually have a Feynman diagram. So the neutrino can upscatter to a heavy neutral lepton state, that's the big N on the right, through a photon. The photon obviously couples to the standard model particles, either the nuclei or the electrons. A differential cross-section can be calculated With this formula, note that this is for nuclear scattering. So the neutrino comes in, scatters off the nucleons in xenon, and then upscatters to a heavy neutral lepton state. The differential cross-section is enhanced by the coherence of the nucleons. So there's a z-squared factor in this formula. If you look at electron scattering, you get a very similar formula, except there's no z-squared enhancement. It's just a z relationship. And there's also, so in the nuclear form factor, or the nuclear scattering, there's a form factor, which we use the Helm form factor. But for electron scattering, you don't have that form factor. You can calculate an event rate in the xenon 1-ton detector by doing an integral over that differential cross-section over the relevant neutrino fluxes that are coming into the experiment. Those relevant neutrino fluxes are primarily the B8 neutrinos for nuclear scattering, but for electron scattering, the PP and CNO fluxes are also relevant. So I'll show how those three neutrino sources generate three different regions of statistical significance of a signal with this model. Getting into the details of how the xenon 1-ton experiment works, a given nuclear recoil event in the detector will generate a Poisson distribution of photoelectrons. So we can model if dark matter, or if a neutrino were to scatter in the detector off the nuclei, it should create this Poisson distribution. It's given by a formula here that has an Ly, which is the light yield of the experiment, and G1 is the gain. We take those values and the formula for the light yield from the xenon 1-ton collaboration group. We can use that Poisson distribution to calculate an event rate of photoelectrons, and then use that event rate of photoelectrons to generate a signal rate. This plot here shows the event rate of nuclear scattering from this model in the xenon 1-ton experiment. This is not the signal rate, so this is just the scattering rate in the experiment. It shows how if that coupling strength D is fixed to a value, in this case 10 to the minus 6 inverse GeV, the event rates go up to a certain recoil energy of maybe 3 or 4 electron volts maximum. And the event rate curves are changed depending on what the heavy neutral lepton state mass is. So we have kind of two parameters to play with in this model: the heavy neutral lepton mass and the coupling strength. And so we can adjust both of those parameters. And if we look at a mapping of that parameter space and the constraints on that space, we can determine how the xenon 1-ton data has constrained this model further from other experiments. So this is a plot showing for tau flavored neutrinos, if they couple or if they can upscatter to this heavy neutral lepton state. There's some existing constraints on this model from IceCube, Donut, and Supernova 1987A. There's going to be future constraints from Super CDMS, which is shown by the dashed line. But the calculations we performed from the null data of the xenon 1-ton nuclear recoil data place some competitive constraints that actually close off a portion of this plot that were previously not constrained. The story is, it's similar calculation for muon neutrinos. So this is the same plot showing for the muon neutrino case. However, the results that we calculated were already superseded by the Charm 2 experiment. I don't have a plot for the electron neutrino case, but those were all, that parameter space is all excluded by other experiments already. So this is looking at the null results of the xenon 1-ton experiment when they published their nuclear recoil data. So we're able to constrain a region of the parameter space. Conversely, shortly after those results were published, or maybe a year later, they published their electronic recoil scattering from a 0.65 ton-year exposure. And that the results they published actually had an interesting signal to them. So this plot shows in black the results from the xenon 1-ton experiment search for electronic recoils. The dashed box lines, that's the actual data from the xenon 1-ton experiment, and the hatch lines, the upper and lower bounds to each data point, are the systematic and statistical uncertainties. The dashed black line shows the background that's calculated by the xenon 1-ton experiment. And then overlaid on that, we have a blue curve. And this represents a potential interpretation of the data from the xenon 1-ton experiment with our model of the neutrino dipole moment upscattering to a heavy neutral lepton state. And the specific signal that's shown here is a best fit area where we found the best value of the two parameters of that model. So the heavy neutral lepton mass and its coupling strength, and calculated what the signal rate would be from that. So you can play with both those parameters, the mass of the heavy neutral lepton state and the coupling strength. Again, you can see how well this model interprets the xenon 1 ton data as you play with those two parameters. So in this parameter space, this is a mapping showing contours of the statistical significance of this model in explaining the xenon 1 ton data. So the three contour colors here are 1 sigma, 2 sigma, and 3 sigma significance of seeing this model explaining the data over background systematic uncertainties. To do this calculation, we did a likelihood function calculation similar to the one I explained earlier. The difference is that we have two parameters to play with. So the test statistic follows a chi-square distribution with 2 degrees of freedom. So the statistics of that are a little different, but the end result is you can map the ability for this model to explain the xenon 1 ton excess to this parameter space. Note that there's kind of 3 separate islands there. So the 3 islands are, so the lowest, the ones on the left with the lowest mass are from the PP flux from neutrinos from the sun. The middle small island is from the CNO flux, and then the higher island is the B8 flux. So this is saying that our signal, or our model, can interpret the xenon 1 ton experiment as being the result of that certain type of neutrino upscattering to a heavy state. But there's constraints to this model as well. So one important constraint, I'll list several, but the first important constraint is stellar energy loss. So if this model of the neutrino upscattering to a heavy dipole or to a heavy neutral lepton state is true, there's a constraint in that if the mass of the particle is below a certain value, it can steal energy away from certain stars as they're being formed. So particularly red giants would be producing these heavy neutral lepton states at high rates. And so the fact that these can steal energy away would affect the stellar evolution of those stars. Another constraint, which I had shown earlier for the nuclear recoil plot, is the supernova 1987A constraint. So I showed that on the plot, but I didn't explain it, so I'll explain it very shortly here. So what could happen if this model is true is the neutrinos could upscatter to this heavy neutral lepton state, and then those heavier particles could escape the supernova and kind of steal energy away and affect the cooling of the core of the supernova. There's an upper limit and a lower limit on this constraint, and that's due to the fact that the coupling strength for this interaction has to be strong enough such that the neutrinos can actually grab the energy, and then it has to be weak enough that they can get away without getting caught again. So it's kind of like a bank robber being able to get into a bank, get into the safe, and then also being able to escape. So the neutrinos, if their interaction strength for this portal are too weak, they're not going to pick up the energy in the first place. If it's too strong, they're not going to escape with it. There's also cosmological bounds on this model. So during Big Bang nucleosynthesis, if this heavy neutral lepton was in thermal equilibrium, it can cause problems to the standard model of cosmology. However, you can get around this by toying with some of the uncertainties in the Big Bang nucleosynthesis in the standard model of it. So if you look at the period right after inflation, as the universe inflated very fast, very quickly, the universe was very cool after that, but then it went through a period of reheating as the inflaton reached its vacuum potential. As the universe reheated, if we kind of adjust the model for that reheating, the exact reheating temperature of the universe can alleviate some of these constraints. Another consideration we have is premature upscattering and decay considerations. So if the neutrino, if there's a neutrino that can upscatter into the state, and that happens if the coupling strength is too high, then this would happen before the neutrino would ever even get to our detector. Whereas with decay considerations, if the heavy neutral lepton state decays very quickly, and if the particle is not moving fast enough to escape the detector before it decays, that could potentially show up as a sort of double bang experiment in the xenon experiment and then be vetoed by the collaboration. So putting all those constraints onto one plot here, we have a nice way of showing kind of the importance of those 3 different islands there. So Unfortunately, the island on the left, which represents the interpretation of this model through the PP neutrinos, is fairly well ruled out, both through supernova 1987A and the stellar energy loss constraints. The other two regions may still be permitted, so they fall inside that little window that's not constrained by those other constraints. But the Big Bang nucleosynthesis constraint could rule these out. So those dashed curves there, which show thermalization of 2 MeV, that represents if the reheating of the universe was 2 MeV versus 5 MeV. Those dashed lines constrain all the regions above them. So we need a better understanding of the BBN mechanism and model to really rule out the regions. And for our analysis, we didn't get far enough to analyze it any further. We proposed that a much more detailed analysis would be needed to totally rule these parameter spaces out. But unfortunately, it looks like our best fit region, which is the top right area there with caused by the B8 neutrinos, could be ruled out by Big Bang nucleosynthesis constraints. The third model that I want to discuss is a dark matter to neutrino interconversion model. So this is a model by which a dark matter particle couples to neutrinos through a scalar mediator. Scalar mediator also couples to quarks through the Yukawa coupling. So this can generate a bunch of different Feynman diagrams. 3 relevant ones are shown here. So a neutrino could scatter off of standard model nuclei and convert into a dark matter particle. That's the first figure, A. The middle figure shows kind of the reverse, where a dark matter particle could come in, scatter off standard model particles, and then convert into a neutrino. And then the third diagram there shows if dark matter particles could scatter off of neutrinos or annihilate to neutrinos via that coupling between dark matter and neutrinos. So on these 3 different diagrams, the rates of these occurring depend on the coupling strengths. For the first 2 diagrams, the rate of occurring depend on the coupling strength of both parameters in the Lagrangian. So this Yx and Yq value both enter into the rates for those first 2 Feynman diagrams. For the last Feynman diagram, the only rate that, or the only coupling strength that affects the rate is one of them, the Yx value. These different Feynman diagrams map to different constraints on the model. So the first Feynman diagram is constrained by experiments like neutrino searches, like coherent, where they're looking for neutrinos to deposit energy into a detector. The second Feynman diagram is constrained by experiments like direct detection experiments, which look for dark matter depositing some energy into a detector. And then the third Feynman diagram is primarily constrained by kinetic decoupling of dark matter in the early universe, which I'll talk about a little bit. So yeah, we can look at, again, a way of looking at the parameter space that's excluded for this model. So this parameter space shows the dark matter mass on the horizontal axis, and then on the vertical axis, kind of generic cross section that describes the coupling strength of both terms in the Lagrangian. So the parameter space here is ruled out by several experimental results. So for the higher masses of dark matter, the direct detection searches like Dark Side, Crest, and Borxino, and Xenon 1-ton experiment rule out some parameter spaces. For lower dark matter masses, the parameter spaces are ruled out by neutrino searches like Coherent and from kinetic decoupling. So to explain kinetic decoupling a little better, so if dark matter and neutrinos are kinetically coupled in the early universe, and this extra interaction beyond the standard model interaction keeps up, and the dark matter becomes kinetically decoupled later in the universe, this affects the kind of distribution of dark matter in the early universe and the kind of seeds of the first gravitational wells forming, and then the formation of galaxy structure formation later on. So this kinetic decoupling is really a cosmological bound on this coupling strength. I should note in this first plot, so there's an additional unknown parameter of this model, and that's the ratio of the scalar, or the ratio of the scalar particle's mass to the dark matter mass, or just, I guess, the mass of the scalar particles. So the constraints that you calculate change if you change that scalar particle's mass So the first plot was if the scalar particle had a mass of 10 times the dark matter particle, and this plot shows if it has 3 times. Another constraint we have to worry about are bounds from terrestrial dark matter scattering. So we looked at what would happen if this model allowed a dark matter particle to scatter off some kind of any kind of atoms in the Earth. It should produce a neutrino flux from this interaction. So this could happen in any kind of lump of regular matter, so the Earth or in the sun. So you can calculate a flux rate of the neutrino productions from this Feynman diagram, determined by the interaction cross section and the local density of dark matter, the volume of the target, which is either the Earth or the sun. And then you can look at the flux rate of that neutrino signal at the detector, which is based on how far away the detector is from the source being created. So we found that the potential to create a significant neutrino flux that could be seen by a detector is much more constrained by the flux of neutrinos happening from this occurring in the Earth than from the sun. But what we found is that the flux of neutrinos is still many orders of magnitude less than other neutrino fluxes from like the solar neutrinos. So this constraint didn't cause any problems on the model, and it didn't really lead to any other constraints in addition to the other ones that were shown. Another plot that shows kind of a parameter space for this model looks at the coupling strength Yx. This plot looks a little different because it doesn't have, so Yq is a fixed value for this plot instead of being an adjustable parameter as it was in the other plot. But you can put constraint curves on this plot as well. So those are the 3 models that I looked at so far. To do some future research in these models, I'd like to look at, for the generic interaction, several things. So lowering the ionization energy of germanium, as Dr. May has looked at, by adding doping to the germanium crystals, you can lower the ionization energy and potentially search for lower dark matter masses. Also employing annular modulation data. So the astrophysical model that I used had did not look at how the Earth moves around the sun and how a signal would be annularly modulated. So the signal rates that I was looking at were so low, it was of the order of just several events. So you would need significantly higher exposures to look for this kind of a signal of a modulation in the data. Improving the model we used for converting recoil energy to a signal. I think this is really important because the Lindhard model has a lot of uncertainties, especially at the low recoil energies that I was looking at. So improving that model would improve our understanding of the backgrounds from neutrino nuclear scattering. Considering directional recoil detection, so this is obviously a really good way to reject backgrounds from the sun. However, it's really hard to do, probably impossible for germanium detectors. The astrophysical framework could be broadened, so we could look at, instead of just the regular Gaussian distribution of dark matter, we could look at some details and structures such as the Sagittarius stream. And then we could look at how could we use data from a potential signal to quantify the impact of neutrino uncertainties on our understanding of the model. So if neutrino uncertainties were lowered, or that our understanding was improved of neutrino uncertainties, we could have a better idea of how we could calculate parameters of this model in the event of a signal, such as the mass and cross section. Another big unknown in this first model was the actual form factor of the interaction. So what the Feynman diagram looks like, what the mediator mass is, what kind of data would we need to be able to put some more details to the model instead of just having a generic model. For the second area of research that I did, the neutrino dipole portal, obviously future experiments were going to provide additional or increased exposure and better lower recoil energy thresholds. It'll be exciting to see what data comes out from these experiments. Potentially, you could do a dedicated search of the signals from xenon 1-tons. So by this, I mean not just veto all the events that would of the particle decaying in the detector, but also try and look for an event in which the heavy neutral lepton state would actually decay in the detector. Future experiments like super CDMS are going to provide data on this or constraints on this model as well. This plot shows as a function of exposure what the constraints on the coupling strength would be from super CDMS. So this plot shows up to almost ridiculously high exposures beyond what Super CDMS proposes to run. However, it shows qualitatively how there is kind of a limit to what Super CDMS can see. As the exposures get really high, the background from neutrinos cause the detector search to plateau. For the last model I talked about for dark matter neutrino interconversion, some future research that could be done. Again, if detectors have ultra low thresholds, there's going to be exciting data coming which would affect this model. Data from the coherent elastic neutrino nuclear scattering, such as the coherent experiment, Connie, CONUS, and Nucleus. So the data coming from these experiments will have an impact on this model as well. So that's kind of the first ideas I have for those three models for future research. An additional model I'd like to look into, and I mentioned this in my comprehensive about a year ago, but I didn't get a chance to look at it over the past year, is CHAMP particles. So this is a fractionally charged massive particle. I guess the acronym is CHAMP, so it's a charged massive particle. Could dark matter potentially have a fractional electric charge, and could it potentially, through that electric charge, have a flux of maybe a very small number of them, but very high energy particles from boosting mechanisms such as Fermi boosting from supernova or from cosmic ray collisions? How could we probe this model? So this is a theoretical model that could be searched for, and though only a small fraction of the particles could be boosted by these mechanisms, we could potentially see them due to their high energy levels. There are constraints on this model that we know of, but we could alleviate those by toying with some of the parameters of the model, such as the population of the CHAMPs being a small fraction of the dark matter population. There's also models by which the charge of these particles is temperature dependent. So in the early universe, the charge could have been less than what it is today, such that we could avoid some early universe constraints. So just in conclusion, I just wanted to mention how much I enjoyed this research, why I find it interesting. So this research into beyond standard model interactions, I find interesting because it encompasses a wide framework of physics. So you're looking at scales from astrophysical scales all the way down to the Planck scale, so very grand scales to minute scales. It touches on many different areas of research, from fundamental theoretical physics to experimental details of experimental detection, to astrophysical, to cosmology, to even grand unified theories. It's very exciting that it touches on many different areas of research. It's an exciting field to be in as well because the technology keeps improving on these detectors and we're getting a wealth of new data. As I was doing this research, we published a paper on the nuclear recoil search from the Xenon 110 data, and then it was really exciting to see that a few months later they published their electronic recoil data, and that could actually be interpreted through one of the models that we had worked on. So yeah, it's an exciting field to be in. I hope to continue research in this field, looking at new models and continuing research on the models that I've looked at so far for the next few years. And I want to just make a few, shout out a few acknowledgements. So I wanted to thank Ian for being my advisor on this project and for his help along the way, mentoring me. So I really appreciated his both technical expertise as well as his just mentoring along the way. To my family and my wife Danny here today. So thanks for coming along and for supporting me along the way too. And finally to the University of South Dakota. So I really appreciated the opportunity I was given here, and the 4 years that I spent in classes and with a research assistantship was much appreciated. With that, I will leave it open to any questions that you might have.
Hi, this is Wenqing. So Jason, congratulations for your achievement and the nice work. I have a few questions about the neutrino portal model. You mentioned the constraints, but can you talk about the support from other perspectives? Why this is motivated? Second question about it: why isn't this interaction spin dependent? Seems that it's a spin independent in your model. And the third question is an unfair question, but I think the excess xenon one-ton Sol is due to tritium decay. So how do you compare two models or two theories? Yeah. Thank you.
Okay, yeah, so I guess the first question was kind of the motivation for this model. So it's kind of tied into the fact that there's beyond standard model physics, there's a sign of that from neutrino physics in the fact that, so neutrinos have a mass and we don't know how they acquire a mass. And so there's been many models that have been postulated that the neutrinos could have a right-handed neutrino counterpart. So that's slightly different than this, this model, but this model at least is kind of along that path of a way that we can touch on the kind of the uncertainties in the standard model. And there's some motivation to know that there are new physics beyond the standard model for neutrinos in that sense. Yeah, the second question was about the spin independence. So we didn't look at the difference between spin independent versus spin dependent. That could be some future research for this work. And I think the third question was about tritium. Yes, maybe I should have said that explicitly. So yeah, I wasn't saying that our model is the solution to this. There's many models that have been proposed that have explained the excess. Our model is just one of them, but probably the most likely one is just that it's tritium background. So the Xenon one-ton collaboration group, in their paper, when they explained the excess of events, they did kind of parameterize their uncertainty in tritium, and they showed that it was definitely a possible source of the signal. So I don't know when we'll be able to know for sure whether it is tritium or something else.
Okay, thank you, and congratulations again.
Thank you.
Hi, Jason, this is Dong Min. Congratulations. You know, you provide a very nice presentation. So I have a few questions, maybe just ask you to clarify some questions I have. So can you actually go to your slide number 9? Yeah, here, so these shows the total number of events on your y-axis, and then your x-axis is mass of dark matter. So when you calculate for electronic, you know, of course, the interactions between dark matter and the electrons on the orbit, and the dark matter and the nucleus. So what is the velocity you consider for orbital electrons? Do you consider group velocity for these orbital electrons, or you just consider single electron velocities, you know, for the orbital electrons?
Yeah, so the model, or the way that we did it, was using this previously calculated work by some other people that parameterized the whole wave function of the germanium atom. So the momentum transfer between each electron is encoded in this F ion factor. So the valence electrons versus the inner electrons, they all have a different wave function structure, and that's all encoded in this F ion term. So we do the calculation for each electron specifically, and for each electron, we do it for each possible momentum transfer to calculate the differential rate. And that calculation is done using data from other published work from someone else. So there is some, obviously it's not a full treatment of the, it doesn't have all the details of the wave function in it, in that there's kind of there's a resolution to the momentum transfer that's encoded in this data we used. But it is a very good way of estimating or calculating the rates, which take into account the whole wave function structure of the germanium atom with some coarse graining to the data in terms of the momentum transfer. Did that explain it well?
Okay, thank you. All right. So my last question actually is slide number 442. Can you go there? So with the neutrino dipole model that you were talking about. Yeah, here. So my question here is that how that neutrino actually cup to xenon nucleus through a photon you were talking about. So what type of photon is that mediator?
Just a regular photon. So, oh wait, this is the neutrino dipole portal. No, this is a dark photon. So
Right. So that's why I was thought that because you didn't see this darker photon, I thought there must be a darker photon you're talking about here.
great. Yes.
Okay. All right. Okay. The last question I have is that can you go to slide number 49? Yeah. So this is yeah. Of course, this is something that Wenqing also asked you, and maybe you know, I think when you feed your theoretical model into Xenon one-time data to explain this axis of events they just recently released in the Nature paper. That sounds like, it seems to me it fit the data well, but obviously there are different discussions going on in the field that could explain the axis better. So it's natural that people propose that the tritium production in Xenon in terms of cosmogenic process could contribute this excess of events, which they did not take into account when they published the paper in Nature. But I think now they're considering it because I know that they've been calculating these kind of cosmogenics production using our paper. We published it a few years ago. So I think it may be a more natural explanation here when they take into account the tritium decay rate here.
Mm-hmm.
So how do you think about that?
So could you repeat that, just that last sentence?
Well, I think it may be more natural to explain their observation here using tritium decay, because tritium production through cosmogenics, this is cosmogenic production when xenon on the surface, right?
Yeah.
So the xenon has a half-life that actually is a pretty long half-life there, right? So it's about 12 years, right? So when they transfer to the underground, so xenon's, one-time experiment would observe these kinds of tritium decay events when they have very low energy threshold there.
Yep. Yeah, I think definitely it's more natural. It's not as exciting to explain it with tritium as it is with this, but yeah, I think, I guess obviously in all these searches, they're at the cutting edge of technology. So if they're going to get a signal like this, like they did with Xenon 110, there's going to be a lot of work going into finding out whether it is new physics or whether it is just some unknown background. So yeah, I think that's where we're at with Xenon 110. It's nice to be able to provide some explanation with new physics, but we're not saying that this is the solution at all. We're just saying this is one of many possible solutions that could explain the data, which may unfortunately just actually be an unknown background like tritium.
Okay, so is this work published already?
This work is not published. It's under peer review right now, I believe. Is that right, Ian?
Yeah, that's right. This is on the archive, so it's publicly available, but
Yes, publicly available. I see. Okay. Did you actually receive any comments from Xenon 110?
No, not yet.
No, not yet. Okay. All right. Thank you.
Yeah.
Very nice presentation. Congratulations.
Thank you.
By the way, this is Bai from School of Mines. I do have some questions, but I want to make sure, do we have a separate question session after,
Yeah.
I mean, just among the committee members?
Yeah, we have that afterwards.
Oh, okay. I can wait to ask later.
Okay. Okay, so Tupender here has asked me to go to slide 46, so I'll repeat his question. Yeah. Yeah. So Tupender has noted that the so for the Tupender has noted that for the heavier mass of the neutral lepton state, the recoil spectrum is heavily suppressed, and that's due to the fact that just kinematically this this heavy neutral lepton state isn't accessible if it's too high in mass. So the event rate for creating this gets suppressed due to the fact that the velocity of the dark matter has an upper limit, the escape speed of the galaxy. So it's tied to the the mass of that heavy neutral lepton state. Obviously, if you go to very, very low masses of the heavy neutral lepton state, it's easy to upscatter into that state because there's no kinematic requirements to have enough energy to upscatter into that state. Yeah. Yeah, so Tupendras asked, which of these three models is the most competitive in terms of the bounds? So the three models all map kind of, they're different parameter spaces because the models are all different. I think the neutrino dipole portal model, it was interesting that the work we did actually mapped some constraints in a window that was previously unconstrained. So you can see here that there's this little window between the supernova 1987A and Ice Cube. So it was interesting that this model could constrain that region slightly. Super CDMS will supersede that when they, as the dash curve shows, when they're finished their data collection. The first model, which is the generic interaction, didn't really constrain any parameter space. It was more like parameterizing how could future direct detection searches search for this model, and what are the limits of discovery of future searches. Yeah. Any more questions from the audience?
If I can make another very general question, how do you distinguish stereo and neutrino with net dark matter or other types of net dark matter from the cosmogenic background?
Sorry, can you repeat that, Dr. Zhu?
Yeah, how do you distinguish stereo neutrino with other types of dark matter from cosmogenic background, a cosmic wave background, sorry.
The cosmic microwave background?
Yeah.
So how do you distinguish the stereo neutrino from other dark matter? So this is not proposed as a dark matter, a solution to the dark matter problem.
Right. So sorry, my question was not entirely on topic. It's a little bit off topic. Like in general, from theoretical perspective, what kind of properties you would need to distinguish the two?
Yeah, sorry, I don't know how to answer that question. I could get back to you though.
No, I think it's it's a pretty hard question. So yeah. it's not it's off topic. Yeah.
Okay. Well, thanks. Yeah. Yeah, I'd like to talk to you about that sometime. That would be a good discussion. All right. Well, thanks to everyone for coming, the general audience. So I think at this time, maybe we can ask the general public to leave and open questions to just the committee. Yeah, maybe take 5 minutes or so and we'll reconvene at quarter after, in about 5 minutes.
Yeah, thanks. Sounds good.
I like this 5 minutes.
Go.
But this is not general audience questions that we are taking 5 minutes.
Thanks. See ya. I'll try and talk to you afterwards.